It's 5 o'clock. Let us start the today's lecture. So, a warm good evening to all of you. I trust audio video is okay.
Yes, sir.
So, welcome in next lecture of Math F242 Operation Research. Last time, I have given you idea about the failure time distribution which follow the exponential distribution. And very important result I have shared with you. We have the three equivalent statement that device has the constant failure rate function, means failure rate will not decrease or increase. Life length of a device has an exponential distribution, and device is as good as new one. So these three statements are equivalent statements. They in general use as a synonyms to each other. Now next, related to the reliability, we have the very important distribution known as the Weibull distribution. So next failure time distribution is the Weibull distribution. So for the Weibull distribution, the hazard rate function is given by zt is equal to beta upon eta t minus alpha upon eta to power beta minus 1. When t greater than alpha, otherwise it is 0. Here beta should be positive, eta should also be positive, and alpha should be non-negative. So zt is the decreasing function when t is it is a decreasing function of t when beta is less than between the 0 and 1. It is an increasing function when beta is greater than t. So later on I will discuss where we have the use of this. But the hazard rate function for the Weibull failure time distribution, z2 is equal to beta upon t minus alpha upon eta power beta minus 1. So you know that when zt is known, when zt is known as beta upon eta t minus alpha upon eta power beta minus 1. This zt is known to you if you have to compute the reliability. So by the theorem 6.2, you know that what is the reliability? E to power minus integral 0 to t zs into ds. For the convenience, and here it is written to you t greater than alpha. For the convenience, we are taking that alpha is equal to 0. Right? Later on, I will tell you what is the alpha. But for the convenience, here I am taking the alpha is equal to 0. So when the alpha is equal to 0, it will become integral 0 to t z is beta upon eta t minus alpha upon eta and beta minus 1. So this can be written as e power beta upon eta, can you take common? Now integral 0 to t, right? And it is the t minus alpha upon eta power beta minus 1. This can be written as e to power minus beta upon eta, and integration will be the t minus alpha upon eta to uh, power beta upon 1 upon eta, and right limit will be the 0 to t. So beta upon eta you can cancel out. So this will become e to power minus, right, e to power minus t minus alpha upon eta, right? E to power minus t minus alpha minus eta, and when we put the 0 minus e to power minus, when we put the e to power, or just you don't take the alpha is equal to 0. If you take the alpha is equal to 0, at that time when we have the basic formula this, so this will become e to power minus alpha to t zs into ds, because t you are defining, right, time you are defining for greater than alpha. So instead of the 0 to t, now you will take the 0 alpha to t. So when we take the alpha to t, so here it will become the alpha, here it will become the alpha, and here it will become the alpha. So it will give you e to power t minus alpha upon eta minus 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 plus, so plus alpha upon eta, plus alpha upon eta, right? This we can write. So this is the reliability. And if you have to compute the ft is what?
So,
Ft is the, by the same formula, zt into
excuse me,
rt.
sir. So,
Huh?
sir, it is t minus alpha by n whole power beta. So, the
Huh.
limits will change. Right?
Yes. It is whole power beta. The same thing will come. It's better here you write. So beta. Yes,
Sir, will
here it
alpha
will
not
come.
cancel out?
Alpha minus alpha will be the 0. So it will 0. So this will become, just wait a bit. Here you write the 0 to power this. So e to power minus t minus alpha upon eta power beta. Clear? So this is the reliability. So when we have the ft is equal to what? zt into rt by the same theorem. zt is given to you as a zt is given to you as a beta upon eta, beta upon eta t minus alpha upon eta power beta minus 1, rt is equal to e to power minus t minus alpha upon eta to power beta. Right, so this is nothing, this is the pdf of the Weibull distribution, right? This is the distribution of the Weibull. So here we have the rt is equal to integral minus 0 to t zs ds. So here the rt will come e to power minus t minus alpha upon eta to whole power beta for the t greater than alpha, and zt is equal to this, so ft is equal to zt into rt. So here directly we can write, and it is the pdf for the, right, this is the pdf for the Weibull distribution. So now in this case, most important to understand what is the eta, beta and alpha. Eta is the scale factor, beta is the safe factor, and alpha is the guarantee time or shift parameter. Means your reliability will start from the alpha, right? This is the guarantee time. During the guarantee time, we have the replacement of the device. So your reliability will start after the time alpha. So here that's why we are taking the zt for t greater than alpha. Alpha represents the guarantee time. During the guarantee time, if there is any failure, we have the new product. So actual reliability will start from the alpha time. And beta is the safe factor. So what is the meaning of the safe factor? Means in the initial phase, of the bathtub. What is the initial phase of the bathtub? We have the shape like this. We have shape like this. So when beta is less than 1 and alpha is equal to 0, then it represents the initial phase of the bathtub, because here the zt is decreasing. When beta is near to 1, when beta is near to 1, then it is more or less constant. It is more or less constant. So it represents the useful phase of the bathtub. Useful phase of the bathtub you can represent using the exponential distribution also. For the exponential distribution also, z is constant, right? Z is constant. Here when we take the beta near 1, then also the shape is like this. When beta is greater than 1, then its shape will be the increasing. That's why the beta is known as the shape parameter. And for the it represents the phase third or old phase also. Normal distribution in general also used for the old phase also. So you can see the Weibull distribution has the characteristic to represent the all the three phases of the bathtub by taking different values of the beta. Beta less than 1 means up to here portion we have the beta less than 1. For this, beta near to 1, and for this we have the beta greater than 1. That's why the Weibull distribution is most important distribution for the reliability theory, because it represents the all the phases of the bathtub. Any doubt in understanding the alpha, beta, eta, and PDF, CDF, PDF and reliability, ZT?
So can you show what each of them represents? Eta, beta, and
What?
alpha. Can you show the slide which shows eta, beta, and alpha?
Right. Important thing is here to understand the alpha. Alpha means here the failure start. Failure start after the time alpha. Right. Then the failure will start. Up to the alpha, if there is any failure, we have the new device, new product. So wherever for the device we are talking for guarantee period, we can use the Weibull distribution. Exponential distribution is useful for the useful phase when the failure rate is constant. For that only we can use this. Let us have some question. Determine the MTTF for the mission time. Mission time is our objective to run the device up to the 1000 hours. Mission time 1000 hours life. If the test data on such component gave the item to fail as shown in table. So you have the data of the 10 devices of same devices, and time to failure of these 10 devices are given here: 807, 820, 810, and so on. Our mission time is 1000 hours. So from here, this is the time to failure. So from the time to failure, you can easily compute the mean time to failure. Mean time to failure, commonly known as the MTTF. MTTF is what? It is the arithmetic mean of the time to failure. So 1 upon n summation of fi. So 1 upon 10 into 807 plus 820 and so on. So right, it will come the 837. So 837 is the mean time to failure, means average of time to failure. So reliability, here when we say mean time to failure, so now we are saying it is a constant, and we have seen for the exponential in the exponential distribution, we have seen if the MTTF is the MTTF is nothing, it is equal to the 1 upon lambda, where lambda is also constant. So MTTF is nothing. It is a 1 upon lambda in case of the exponential distribution. So we are assuming that when the failure time, when the lambda is constant, zt is constant, then we have the MTTF constant. So wherever we have this MTTF as a coming as a constant, there you assume that it follows the exponential distribution. So MTTF is equal to 1 upon lambda. And and for the exponential distribution, you know that reliability is what? E to power minus lambda t. Lambda is equal to 1 upon MTTF. So it will come the e to power minus 0.0012 into t. And our mission time is what? Our mission time is 1000 hours. So when we multiply this, so this much reliability should be with the device, right? So that we can achieve the, at least this much reliability should be there, so that we can achieve the mission time of 1000 hour for the, for that device. If the failure rate is not given in that form, if it is given in the interval form, then how we can write? The same type of the question, only the difference is failure time is given in the interval. The live testing data of 1000 specimen of a particular device are given below. Now we have the 1000 data. There we have the 10 devices. Now we have the 1000 devices. So generally for the 1000 devices, we present the data in class or in interval. So when we have the data in class, right, or in the interval or in range, then how to compute the MTTF? Determine the MTTF of a device for an operating period of the 1000 hours. So time interval. So zero device fail below the 1000 hours. 175 device will fail between the 1000 to 1050. 400 in 1050 to 1100. 300 devices fail in 1100 hours to 1150, and 125 fail in 1150 to 1200. So if we have this thing, it means we assume that 175 device fail, 175 device fail between the 1000 to 1050. Here we assume that all these 175 fail at this point. We fix that all this 175, wherever it is failing, it is immaterial. Now we are assuming that it is failing at the 1050. So total average will become mean time to failure, right? Total mean time to failure will become the 1 upon 1000, right? 1 upon 1000. Now 175 will survive up to the 1050, right? 400 fail at the 1100, 300 fail at the 1150, and 125 fail at the 1200. So it will come the 118.75 hours. Clear? See again, I am saying that all these 175 device fail up to the time 1050. All 400 devices fail up to the time 1100. All the 300 devices fail, right, up to the time 1150, and all 125 devices fail up to the time 1200. What is the reliability of a component for an operating period of 200 hours? You require, if your mission time is 200, then what is the reliability? Having the failure rate 0.4 into 10 to power minus 5 failures per hour, lambda is given to you. 5000 such items are tested. How many times it fail in 200 hours? So out of the 5000 items, how many will fail? So here lambda is given to you as a 0.4 into 10 to power minus 5 failures per hour. So you know that if lambda is this, right, it is the constant. It is constant. Then reliability, you know, reliability will be the e to power minus lambda t. So when we have the e to power minus lambda t, so it will become the e to power minus 0.4 into 10 to power minus 5 into t. Now you want the reliability with mission time 200 hours. So reliability for the 200 hours will become the e to power minus 0.4 into 10 to power minus 5 into 200. So it will give you 0.992. So 0.992 is the reliability at 200 hours. Now at the zero time we have the reliability 1 and total 5000 uh, devices are tested, start to test. Now reliability at the 200 it is given to as a 0.992. So how many will remain? So how we can compute? So let n naught be the total number of component in the test 5000. Ns is the total number of components survived. Nf is the total number of component fail. Right? So Ns is equal to n naught into RT by the relative frequency approach, because you know that what is the RT? It is the number of the survived at the 200 and number of the item put at the initially. So it will become the right, and number of the survived at the 200 will be the n naught into RT. So it will come the 4996. So total number of the failure will become the n naught minus ns, that is the 4 item. So 4 item will fail in testing in 200 hours. Now the Alpha company manufactures gizmos for use on busy. Time to failure in years. These gizmos has PDF FT is equal to 200 upon T plus 10 to power 3. So here FT is given to you. FT is given to you 200 upon T plus 10 cube. Right. Find the reliability function and determine the reliability of the first year operation. So you know that what is the reliability? What is the reliability? Reliability is integral t to infinity ft into dt. So t to infinity 200 upon t plus 10 cube into dt. So it will become 100 upon t plus 10 square t to infinity. So 100 upon t plus 10 square for t greater than 0. So that is the reliability, right? Reliability of the device. Then after you have to compute reliability at the first year, means R of 1. R of 1 will be the 100 upon 1 plus 10 whole square, 100 upon 121, and its value is 0.8264. Its value is 0.8264. So in this way we can compute from the given function the reliability. Then after you have to compute the find the MTTF. So when we have to compute the MTTF, so you know what is the formula of the MTTF? MTTF, that is the ET integral 0 to infinity of RT into dt. So it is the integral 0 to infinity RT we have computed as 100 upon T plus 10 square into dt. So this will become 100 upon t plus 10, right? 0 to infinity. So this will come, I think, 10 years. 10 years, right? So here it will be the reliability 0 to infinity RT dt. So this will come the 10 years. Clear? Then after, what is the design life if the reliability is 0.9? So what is the design life if the reliability is 0.9? So we know that RT is equal to what? RT is equal to 100 upon T plus 10 whole square. So 100 upon design life, you assume that let it is the TF plus 10 whole square, and it is given to you as a 0.9. So this will come 100 upon 0.9, right? TF plus 10 whole square. So TF will come 100 upon 0.9 power 1 by 2 minus 10. That is the design life. So this will come as a 0.5409 years or 197 days. Clear? Then after, it is very good question. Find the failure rate. Failure rate means ZT or hazard rate, right? So find the failure rate. So we know that ZT is what? ZT is FT upon RT. And what is the FT? Minus of R dash T upon RT. RT we have computed as as 100 upon T plus 10 whole square, and minus and here R dash T. So R dash T will come minus 200 upon T plus 10, T plus 10, right? So here the ZT will come. ZT will come so the ZT will be the 2 upon T plus 10. 2 upon T plus 10. Actually, in slide we have the not good notation. That's why I'm writing here. Right? 2 upon T plus 10. So this is the ZT. So from the ZT, in the last part, they are asking is this is the is gizmos experiencing the beer out? What is the meaning of the experiencing the beer out? Anyone can answer? What is the meaning of the beer out?
Phase 3.
Eh?
Device reaches phase 3.
What is the at that time? What is the status of the ZT failure rate? Failure rate is increasing.
Increasing.
Correct. Yeah, correct. Failure rate is increasing. So for seeing the whether the ZT is increasing function or decreasing function of time, how we can check?
Differentiate ZT.
Yes, differentiate ZT, right? So we have to compute the ZST. So this is the ZST. So ZST is what? Minus 2 upon T plus 10 whole square. And because T is positive, non-negative, right? T is non-negative. So minus 2 upon T plus 10 whole square will be the negative. So this implies that ZT is decreasing function of time. So gizmos does not bear out. right? It is coming negative. It means does not, gizmos does not bear out. If the jet t is positive, increasing function of time t, then we say gizmos bear out with time. Clear? So sometimes we can have this type of the question also. Now, this is also very important question. Easy but very important. The mean time to failure of a particular type of the component is 800 hours. So MTTF is given to you. MTTF is given to you as a 800 hour. What is the probability that similar component will fail in operating time, of 200 hours, in operating time of 400 hours? So if MTTF is given to you 800 hours, what is the lambda? Lambda at that time always we assume as a 1 upon MTTF. 1 upon MTTF means 1 upon 800. So when we assume this, so here what we have to compute? It lasts up to the 200 hours. It means we have to compute the reliability at 200. So reliability at 200 means e to power minus lambda t. T is 200, lambda is 1 upon 800. So e to power minus lambda t, or e to power minus t upon mttf. So it will come 0.7788. 0.7788. Similarly, for the 400 hours, it is the 0.6065. For the 800 hour, 0.3679. And for the 1000 hour, it is the 0.8265. Here, the important result is this. Hence, if the component is put in the use for the period equal to MTTF, probability that it will function properly only the 36.8. Only the 36.8% device achieve the mean time to failure. Whatever the mean time to failure assigned by the company, only the 36.8% device achieve this. Right? That conclusion you can do from here, or nearly 37%. Right? 37% device cross the mean time to failure of a device. तुमने देखा होगा, इसलिए बहुत कम लोगों के टीवी बहुत पुराने पुराने अभी हैं. अदरवाइज जनरली मतलब 63% टीवी जल्दी खराब हो जाते हैं. Now, so till now we have talked about the reliability of the system, reliability of the subsystem, reliability of a unit, reliability of the device. Now we have not taken care the arrangement of these devices. In the system we have the various subsystem. In the subsystem we have the various numerous devices. So how they are arranging, we have not talked about that. Whether their arrangement is important to increase the reliability. So reliability of the system in terms of the reliability of its component means if in the system we have the n components, so how they are arranged means how we should arrange them so that we can get the maximum reliability. So for that we have the two type of the arrangement. Basic arrangement, we have the more arrangement, but most basic arrangement are series and parallel. So we have the two basic arrangement of the component, series system and the parallel system. So let us start with the series system. Here I will tell you the theory of the series system and problem 6.7 and problem 6.8 simultaneously. Right, I will discuss the series system. Right, what is the series system? Then I will tell you the problem number 6.7 from your book and problem number 6.8. So let y be the life of n independent series system with n component. Y is the lifetime of the system in which n components are arranged in series. Find the PDF CDF by also prove that hazard rate function of the system is sum of the hazard rate function of its component. In the 6.8, consider n component independent series system given that these components have constant failure rate lambda 1, lambda 2, lambda n respectively. Find the reliability of the system, hence prove that failure rate of the system is also constant and is equal to the lambda 1 plus lambda 2 plus lambda n. What is the lifetime distribution of the system? Also express the mean life of the system mu s in terms of the mean life length mu1, mu2, mu n of its component. So one by one, I will discuss all these things. So first, what is the series system? So here, when the components are arranged, a system consisting of the certain number of components, say n, which will function satisfactorily if and only if all the n components function satisfactorily is called the series system. Means here, what is the meaning of the series system? Here the components are arranged in a series form. Are arranged in a series form. If any component fail, we say whole system fail. Right? Then we say whole system fail. Anyone can tell where you have seen this example?
Serial lighting.
Pardon? In
Serial
लड़ियां
lighting.
देखें, हाँ दिवाली की लड़ियां देखें, दिवाली की जो लड़ियां होती हैं इधर शादी शादी ब्याह में जो लड़ियां लगाई जाती हैं, यदि एक बल्ब भी खराब हुआ तो पूरी की पूरी लड़ी खराब हो जाती है. That is what? That is the series system. If any one component fail, whole system will fail. That is the series system. So here we have example. Series system is the string of light bulb in marriage decoration. So in this case, here we have the n components arranged in series. If one component fail, then then whole system will fail. Means for the functioning of the system, it is necessary that all n component must work. Clear this part? Now, if I say, let us have first component, second component, third component, and let us say n component. They are arranged in the series. Let xi is the life length of ith component. Right? Let xi denote the life length of the ith component, and it is what? It is the continuous random variable. It is continuous random variable. So continuous random variable means characterized by the PDF. So it is the PDF of the life length of the ith component. Fi is what? CDF of the life length of the ith component. Right? RIT is what? Reliability of the ith component. ZIT denote failure rate, hazard rate function of the ith component. Right? So it is the hazard rate function. Right? Hazard rate function. So let xi, fi, capital Fi, Ri, Zi, we are defining for the ith component. Now, this is the complete system. So let us assume, let y denote, it is only given to you, life length of the system. Life length of the system. So when we have the life length of the system, we have to compute we have to compute the PDF of the Y, CDF of the Y, reliability of the system, failure rate of the system, right? And MTTF of the system, MTTF of the system. These things we have to compute. Naturally, the system is comprises with a component, n components. So from here, what is the Y? Y is the life length of the system. How they are related to the life length of the component? Y is equal to how the Y is related to the life length of the component. Anyone?
Minimum of xi.
Minimum lifeline.
Yeah, correct. Minimum of xi, right? Y is nothing minimum of xi, and here all the xi's are independent. All xi's are independent, right? So y is nothing for the y is not in series. In series, it is the minimum of the x1 comma x2 comma xn. Now if you have to compute the PDF, CDF, reliability, uh, failure time distribution, and so on. So first we are talking about the reliability, right? So here we have defined for the component, right? All the xi, y, fxi, ri, zi. Now if you compute the reliability of the system, reliability of the system means rst. Rst by definition it is equal to probability that time to failure y greater than t. So probability y is what? Minimum of x1, minimum of x2, minimum of the x1, x2, xn greater than t. If minimum is greater than t, it implies that all are greater than t. All are greater than equal to t. Since xi's are independent, since xi's are independent, this can be written as probability of x1 greater than t, probability of x2 greater than t, because we know that probability of A intersection B is equal to P of A into P of A into P of B. When the A and B are independent, then A intersection B is equal to P of A into P of B into P of xn greater than t. And what is this? This is the RIT, or you can say R1T, R2T, reliability of the component, and RNT. It means this is nothing, it is the product of RIT, I from 1 to n. Reliability of the system is nothing, it is the product of the reliability of the component. Reliability of the component. Then after, we know that now we have to compute the PDF. So if you taking logarithm on both sides, on both sides, so it will become the ln of RST summation I from 1 to n ln of RIT, right? Product change into the summation. Now differentiate with respect to t. So when we differentiate this with respect to t, what it will give you? Ln of RS means 1 upon RST and r dash t. This will come is equal to summation I is equal to 1 to n, differentiation of this. So ln of x means 1 upon x, then derivative of this r dash it. And what is the r dash? R dash is the fs and rst summation I is equal to 1 to n fit minus upon rit. Now this minus will cancel out. So fst means pdf of the system, or you can say fyt is what? rst into I is equal to 1 to n fit, means you are writing the pdf of the system in terms of the pdf of the component. So that is the pdf of the pdf of the system. Then after having the pdf, we can compute the cdf also. So before the cdf, uh, what is the relation between the ft upon rt?
Z of
What
t.
is the relation between the ft upon rt?
Hazard rate function.
Hazard rate function. So this will give you zst, right? Zst is equal to summation of I is equal to 1 to n zit, means zst is equal to what? Z1 plus Z2 plus Zn. So this is the in the question number 6.7. Let y be the life of an independent series system with n component. Find the pdf and cdf of the y. Also prove that hazard rate function of a system is sum of the hazard rate function of its component. So this we have proved that zst is equal to z1 plus z2 plus z3. Now if you have to compute the cdf of the y, so cdf of the y means fyt. Fyt is what? If you take the joint probability integral 0 to t 0 to t 0 to t for the n component, fs having the n component x1 x2 xn, right, dx1 dx2 dxn. So because the x1 x2 xn are independent, this can be written as, let us do there. So I'm saying that if you have to compute the fyt, what is the meaning of the fyt? Probability that y less than equal to t, y less than equal to t, right? So it is the integral 0 to t integral 0 to t integral 0 to t n times joint distribution. So fs of the variable x1 x2 xn dx1 dx2 dxn. Since x1 x2 xn are independent, so when they are independent, you know the joint densities can be written as a marginal densities, product of the marginal densities. So this can be written as 0 to t f of the x1 dx1 0 to t f of x2 dx2 0 to t f of xn xn dxn. This can be written as 1 minus integral t to infinity f of x1 dx1. 1 minus integral t to infinity f of x2 dx2, so on, and 1 minus integral t to infinity f of xn dxn. And what is this? 1 minus r1t, 1 minus r2t, 1 minus rnt. And so fy t is nothing. It is the product I from 1 to n of 1 minus RIT. 1 minus RIT. So that is the CDF of the series system. Rest part we will do in next class. Right? Question number 6.8. Series system and question number 6.7 I have covered. Rest part I will do in next class. Any doubt in understanding the series system or basic of the probability?
Sir?
Yes.
Sir, I had a question related to inventory models.
Tomorrow at the time when I will see all the means your recheck request, at that time I will discuss.
Sir, not
बस
regarding midsem.
अच्छा चलो फिर जनरल क्वेश्चन तो पूछो.
Yes, sir. I was doing one question. There it was given like it was modeled 8 and continuous distribution, and we need to calculate R star. So we
Continuous means uniform. You are asking
yes, sir,
uniform.
uniform. Yes, sir.
हाँ.
So, sir, R star we will write in integer or it can be in decimals.
Depend over the question. If it is the discrete item, then you have to take the discrete. If it is the continuous item, then you have to take the continuous.
Means, sir, if it is continuous, then we will have to keep it in decimals only.
हाँ.
But sir, then after calculating R star, we also need to calculate the order point. So it will become very difficult if we do it in fraction.
हाँ डिफिकल्ट है लेकिन इम्पॉसिबल नहीं है. डिफिकल्ट तो है, ठीक है, बात सही है, डिफिकल्ट है.
Okay, sir.
डिफिकल्ट तो है, मतलब ये बात सही है, डिफिकल्ट है जनरली. इसलिए इवन डिफिकल्ट तब भी है जब हम भाई डिमांड है. डिमांड हमने कहा कि कंटिन्यूअस रैंडम वेरिएबल है. हमने केवल एक एग्जांपल लिया है, केवल यूनिफॉर्म डिस्ट्रीब्यूशन का. तुम इसी में यदि नॉर्मल डिस्ट्रीब्यूशन लगा दो तभी बहुत कठिन हो जाएगा क्वेश्चन.
Yes,
इसलिए
sir.
हम केवल एक ही पीडीएफ पे काम करते हैं, नॉर्मल यूनिफॉर्म डिस्ट्रीब्यूशन पे. अदरवाइज उसका तो इंटीग्रेशन करना बहुत मुश्किल हो जाएगा ना.
Okay, sir.
तो इसलिए मान के चलो कि कंटिन्यूअस यूनिफॉर्म डिस्ट्रीब्यूशन ही है, मतलब वो कंटिन्यूअस है, डिस्क्रीट यूनिफॉर्म डिस्ट्रीब्यूशन नहीं है उतना, क्योंकि एग्जाम में टाइम भी नहीं आता है ना. यदि तुम्हें अपने लिए कुछ करना हो, कभी रिसर्च के लिए कुछ करना हो, तब कर सकते हो. ऐसा नहीं कि एग्जिस्ट नहीं करता है, लेकिन हम यहाँ कोर्स में नहीं है मतलब.
Okay, sir.
Excuse me, sir.
हाँ. यस.
Sir, in the midsem solution for question 4, only 11 marks has been allotted. It was a 17-mark question.
11 नहीं है, पूरे 17 है. ध्यान से देखो सोल्यूशन, पूरे 17 है.
No, sir. Only 11 marks have been allotted.
चलो मैं देखता हूँ अच्छा क्या है.
And so one more thing in question 5, as you have written that Q star should be multiplied by 30, but if we take the parameters in days or months, Q star is coming 21 only. So why we need to multiply by 30?
Because we are taking the stock in starting of the month. Daily we are not taking the stock ना. In there we have the language कि महीने के शुरू में ही आ जाएगा सामान.
Sir,
क्वेश्चन को
but
यदि ध्यान
it
से देखो.
wasn't like, sir, but Q star doesn't depend on month or day, right?
क्यों नहीं
It's
होगा
anyway
यार?
starting of the cycle, that's all.
नहीं तो साइकिल तो महीने पे ही तो स्टार्ट कर रहे हैं ना यार. क्यों
Sir,
तुम
if we
बीच में
say it starts at the starting of the month, it is also starting of the day, we can tell, sir. Can't we
नहीं,
say
you
like
can
that?
tell if we नहीं, you can tell if I am asking that, if clearly I am writing that it is all the components or means all the inventory we stock during the initial of the month.
Okay.
So with the 21 item you can stock for the month.
Sir, it would depend on demand and everything, right?
कैसे डिमांड पे डिपेंड करेगा बताओ ना. सारी चीजें हमने मंथ पे दे रखी हैं, कैसे डिमांड पे डिपेंड करेगा?
Sir, but when we applied that formula for
मतलब
Q
तुम
star,
खुद ही कह रहे हो कि
all
क्यू स्टार मतलब कहीं तो कुछ लिखोगे ना कि क्यू स्टार मतलब मंथ के लिए है या डे के लिए है, क्या है?
sir, Q star is independent of those things. When we converted
नो नो
all parameters to per day,
अरे तुम नहीं समझ पाए हो. ये नहीं है कि क्वेश्चन इज रॉन्ग. मतलब आधे से ज्यादा क्लास ने किया है ना, उसमें कोई गलती नहीं है. क्यू स्टार फॉर द मंथ वी आर आस्किंग, इट इज क्लियरली रिटन इन द क्वेश्चन. अरे अभी तो चलो मिड सेम है, मतलब ठीक है, चीजों को कॉन्सेप्ट को समझो ना यहाँ पे.
sir, I didn't ask for marks. I wanted to know
अरे यार
the
you
concept.
people are saying diplomatically that I am not asking marks. You are asking for the marks only.
Sir, I need to
Otherwise
know what I should
conceptually
write for
नहीं
compre.
नहीं
That's why I'm
conceptually
asking.
you already know कि you are wrong. Conceptually you know that it is wrong. It is all clearly written in the question that it is for the means month, right? Nothing there is any ambiguity.